Hilfe?
Ja, ich glaube auch nicht. Ja.
Hello everyone, my name is Lavinia Stiliadou. I'm from the Institute of Architecture of Application Systems. Today I'm going to present you the paper that my colleagues and I wrote on exploring the cost landscape of variational quantum algorithms. Quantum algorithms are typically hybrid since quantum devices are error-prone, so we want to limit the time that we spend on them. Therefore, we execute the parameterized ansatz and perform the measurements on the quantum device, whereas other parts, such as the post-processing and optimization, are performed on the classical device. The optimization process is often formulated as a minimization program where we want to minimize the cost function values. Or in other words, we want to find the global minimum of the cost landscape. However, as we can see here, the initial set of parameters will likely not result in a global optimum of the cost landscape. Therefore, our classical device will output a new set of parameters which result in a new measurement result in a new point on the cost landscape. As we can see here, we are going down and we are walking towards the global minimum of the cost landscape. And this process is repeated until we meet some convergence criteria. However, the optimization process often results in suboptimal solutions, and this can be explained by the features that the cost landscape contains. And such features are local optima. What is the difference between a local optimum, a local minimum, and a global minimum? When we can take a look at the two-dimensional cost landscape, which is parameterized by one parameter, then we can see here an example for local minimum and here an example for global minimum. In a local minimum, the gradients points in all directions to an increase in cost, and the cost of the local minimum itself is larger than of the global minimum. This concept also applies to higher dimension. When we take a look at the three-dimensional cost landscape, which is now parameterized by θ1 and θ2, and the color map here is now the cost function values. When we have high values, these are depicted in yellow, suggesting maxima, and low values in blue, suggesting minima. Then we can see that the cost of the local minimum here is larger than of the global minimum here. Therefore, this is the global minimum and this is a local minimum. Such features are problematic for the optimization process since they lead to suboptimal solutions because the gradient is zero at this point and the optimizer might struggle to escape these regions. Therefore, local optima are one example of a problematic feature of the cost landscape. Saddle points also lead to suboptimal solution, and what is the difference now between a local optima and a saddle point? When we take a look now at the three-dimensional cost landscape, you can see here that this point is a saddle point because we have one slope that's going down and one slope that's going up. And therefore, this point is a saddle point and not a local optimum. Since for a saddle point, we don't need that all slopes have to go in the same direction. Therefore, the likelihood that a point becomes a saddle point increases with the number of dimensions because a local optimum requires that all slopes are going in the same direction. Another feature that can influence the optimization process are barren plateaus and narrow gorges. Barren plateaus are flat areas in the cost landscape where the gradients exponentially vanish with increasing number of qubits. We take a look now here at two cost landscape where we increase the number of qubits in this cost landscape. Then we can see that the yellow area is increasing, and this is now an indicator for the flat area. And when we now generate 200 random points on the different landscape, then we can see here that many of these points are nearly uniformly distributed across the different colors. However, in this cost landscape, we have many red points on the yellow area, so on the flat area. And these points are problematic for the optimization process. Since the optimizer doesn't know in which direction it should navigate since the gradients are essentially zero. Another problematic features are narrow gorges since they are very steep and narrow regions in the cost landscape. And therefore, we need to adapt our step size based on based on the size of the narrow gorge. We identified now the four features of the cost landscape that can hinder the optimization process of variational quantum algorithms. However, we need to identify now the characteristics to identify these features. Therefore, we take a look at the frequency. If we have more features present in our cost landscape, then the likelihood of a suboptimal solution increases. So if we have now a cost landscape with many peaks and many values, then the likelihood that our optimizer will output a local peak instead of the lowest peak increases. Therefore, we need to take a look at the frequency of each feature. Then we have to take a look at the gradient behavior. If we have cost landscape which are very flat, then the optimizer might struggle to find the optimal solution, since the gradient gives us an indicator of the direction of improvement. And if we have no information from the gradient, then our optimizer doesn't know in which direction it should essentially navigate. Therefore, we want cost landscape where the gradient points us to the global optimum, which can we see here. Another characteristic that we should analyze is the curvature. And curvature is a concept from differential geometry, and we want to take a look how each point is curved to give an indicator of the size of the feature. Since we mentioned earlier, this narrow gauge are very steep and narrow regions, therefore we need to adapt the step size of the optimizer. Therefore we need to take a look at the curvature. We identified now the three characteristics which helps us to identify the problematic features for the optimization process. And now we need some sort of a description which tells us how frequent are these features, how the gradients behave, and how is the curvature. And for this description we take a look at metrics. And metrics are a concept where we have such a variety and we want to find metrics which actually tackles exactly these characteristics. Therefore we took a look at the literature and we found 4 features which actually tackles frequency, gradient behavior, curvature. These are total variation, Fourier density, the inverse gradient, standard deviation, and scalar curvature. Total variation actually captures how much a function varies across a finite domain A. And what we can see here now is that the total variation actually takes into account the frequency and the gradient behavior, since it's defined as the integral of the absolute value of the gradient. And if we have now high total variation values, that means we have many variation in our cost landscape, which leads us to rough landscape, and rough landscapes are cost landscape in the literature containing many local optima. Therefore we can use total variation to actually capture this. And if we have low total variation values, that means we have less variation in our cost landscape, and therefore we can use total variation as an indicator of flat areas. Another metric are Fourier density, which describes the number of non-zero Fourier coefficients, and it's defined as the ratio of the L1 norm and L2 norm of the Fourier coefficients, which can be retrieved by the discrete Fourier transformation. And if we have high Fourier density values, it means we have sharp transition present in our cost landscape. Such sharp transitions are narrow gauges. Therefore, we need many non-zero Fourier coefficients to actually approximate these steep and narrow regions in the cost landscape. If we have low Fourier density values, that means we have less rough landscape. However, these landscapes can be expressed for rather simple periodic functions. Therefore, the Fourier density values are lower. And if we combine now the total variation with Fourier density, we have actually an indicator for Baron-Cartesian and narrow gauges. Since if we have low total variation values, that means we have less variation in our cost landscape, indicating that we become flat. However, if we have high Fourier density values, it means we have this sharp transition present in our cost landscape, which leads us to the indicator of Baron-Cartesian and narrow gauges, which are actually correlated features. And if we now take a look at the inverse gradient standard deviation, this is defined as the variation of the gradient values from the gradient mean. Then we can see if we have high IGSD values, that means if many gradient values are close to the gradient mean, then the standard deviation here gets very low. And if you divide something, if you divide 1 by something very small, then we get high values. So if we have high IGSD values, it means we have flat areas present in our cost landscape. And if we have many values that differ from the gradient mean, so if we have many variations in our cost landscape, then the standard deviation gets very large. If we divide something by very large, then we get lower IGSD values, which is an indicator that we have many variations in our cost landscape present. We mentioned earlier the concept of curvature. Now we want to take a look at the scalar curvature, which actually defines the curvature of a point on a cost landscape. It is a concept from differential geometry, which actually uses the gradient and Hessian to compute the curvature. And if we have a positive scalar curvature value, then that means we have a spherical shape present in our cost landscape, indicating that we have a local optimum. If we have a negative scalar curvature value, that means we have some sort of a hyperbolic shape present in our cost landscape, then we have a saddle point. And if we have no curvature at all, this is an indicator that we have a flat. We showcase now how the different metrics are working. However, we want to see how they interplay to actually identify the problematic features of the cost landscape. And we applied now our different metrics to the maximum cut problem, where we wanted to solve it using a variational quantum algorithm, QUARA. And the maximum cut problem is defined as the following. We want to find a position of the node set such that the edges between this node set is maximum. And we have now a maximum cut instance of size 5 with 6 edges, and if we cut now along these edges, it results in the following partition. We have 3 nodes in the black set and 2 nodes in the gray set. And if we actually count the number of red edges, then we have a maximum cut value of 5. And this is actually an optimal solution, since if we take now the last edge into our solution, that would not lead to a partition of the node set. That's why this solution is an optimal solution. How did we actually gain our results? We had 3 main phases: the generation, the execution, and then the evaluation of the different metrics. We had in the generation phase the generation of the different maximum cut instances of different size. Then we generated our power circuits, which are parameterized by gamma and beta. And these circuits were then the input for the execution phase. And then the results were taken to actually generate the cost landscape and to evaluate our metrics. Now let's take a look at the different results. We have here now a 2-dimensional visualization of our cost landscape, and each diagram contains now the following information. These are the parameter values for gamma, and these are the parameter values for beta. The color mapping here indicates cost function value. If we have high values, again, these are depicted in yellow, suggesting maxima, and if we have low values, these are depicted in blue, suggesting minima. So if we compare now this landscape with the other 2 landscapes, then we would classify the first landscape as rough, since many local optima are present in the first landscape. And what we can see here now on the last landscape here on the right, that we have only local optima present for gamma nearly 0. And the other local optima are disappearing. Therefore, our cost landscape gets flatter. And how can we identify this flatness of the cost landscape? By the total variation. What we can see is if we increase the number of nodes in our maximum cut instance, actually our total variation values are decreasing, indicating the flatness of the cost landscape. And what we also observe is that our cost landscape gets steeper. We had at the beginning cost function values between -1 and 1, then between -5 and 5, and at the end between -10 and 10. And how can we understand now the steepening? By the Fourier density. And in order to analyze which coefficients are disappearing, we use the concept of a Fourier landscape. The Fourier landscape is defined as the following. We have here at the horizontal axis the values for the frequency f gamma, and here the values for the frequency f beta. The color map here indicates now the absolute value of the complex Fourier coefficients. And what we observe is if we increase the size of the maximum cut instances, many of the frequencies are cancelling out. And we have now for f beta equal to 4 many data points close to each other. And what does it mean? We have now many non-zero Fourier coefficients to actually approximate the sharp transition which we have now present in our cost landscape. And this sharp transition is an indicator that we have now a narrow Gaussian present in our cost landscape. We talked earlier also about the IGSD, and we have IGSD values for each parameter direction. So we have value for gamma and for beta, And if we take now a look at the different values, then we can see that the IGST values are increasing with increasing size of the maximum cut instance. How can we explain? We have now many gradient values that are close to real and mean. Therefore, our standard deviation gets smaller, and if we divide 1 by something small, then we get large IGST values. Therefore, our IGST values are explaining the flatness of the cost landscape. And now we want to take a look at the last metric, our scalar curvature. And for the scalar curvature, we actually decided to use a 3-dimensional plot of the cost landscape to actually showcase the parameter values for gamma, for beta, and the cost function values. And now here the color map indicates the scalar curvature values. If we have positive scalar curvature, this is an indicator for local optima. If we have negative scalar curvature, then we have a saddle point. And what we observe is here now that many of the local optima that we had here at these margins disappear. So our cost landscape gets more flat. However, if we take a look now at the area of the same curvature, here at the yellow area, then we can see, if we map it now here to bigger size, that the area of the same curvature gets smaller and smaller, explaining the steepening of the cost landscape. We showcase now the different metrics and how they can be used to identify the different features that can hinder the optimization process of variational quantum algorithm. Future work will tackle the development of new metrics. We have the concept of scalar curvature, which is defined for the curvature of a point. We want to expand this term of curvature in order to define the total curvature or the total absolute curvature of the whole cost landscape. This will give us more insights into the classical optimization process to enhance the efficiency and accuracy. And now I'm at the end of my presentation, and thank you all for your attention.
Lucille, it's the name, Lucille.
There you go.